This is video 2 of Unit 14. In this video we'll talk about bases, the other class of compounds we are studying in this chapter. So bases produce OH minus. If you recall, acids produce H plus, and bases produce this guy. This is called the hydroxide ion, hydroxide. And some of the properties of bases are that they taste bitter as opposed to acids tasting sour. If you ever tasted soap, for example, soap is a base. You found the bitterness that came from it. If mom had to take care of some mouth cleaning after some conversations that were unsavory. And they are also electrolytes, which means they produce ions. In this case, the ion is hydroxide instead of hydrogen. Now, they feel slippery. Very often you can feel that you have a base on your hands, say in the laboratory, because your hands all of a sudden will feel slippery. This is actually an indicator you have a base and you have to wash your hands. Soap is slippery because soap is a base. And in general, there are no reactions with metals. This is in contrast to acids. Each one of these points essentially is compared to acids. The exception here would be aluminum. Aluminum actually can react with bases. Aluminum is just a very reactive metal from the regular metals. And aluminum will react with bases. All right. Now the formula of the base usually ends with hydroxide, OH. That's how you know you have a base. An example would be sodium hydroxide, as you'll see in a minute. And it turns the litmus paper that we've talked about earlier blue instead of red, as was the case with acids. And it turns phenolphthalein, the indicator that you have to drop into the base, pink. So here, for example, is the base before, and then when you put a few drops of phenolphthalein in there, the whole solution turns pink. You really only need 1 or 2 drops. One drop will turn it this pink. So an indicator is a small amount. You need a small amount of indicator to indicate to you what you have. So here are some examples of bases. We're not going to go into too much detail into each one of these, but notice all of these bases begin or end with an OH, and these two bases do not end in OH. So the OH thing is missing, OH missing in the formula. Now, the OH is there whenever you put these into water. So only in formula. OH missing only in formula. But they do produce OH. And both NH3 is actually ammonia, and ammonia will produce hydroxide ion. This guy here, NaHCO3, is actually baking soda. This is called sodium bicarbonate. Sodium bicarbonate, and it will produce OH minus in solution as well. So these are the 5 common bases that we will discuss and see again and again. Here are some uses of bases. They are used as cleaning products or in cleaning products. Windex is very famous. It contains actually ammonia. And baking soda obviously can be used as a cleaner. They're also used in Drano. Now Drano is what cleans your drains. If your drain gets clogged, you pour Drano in it. Drano has the active ingredient sodium hydroxide, which is a strong, dangerous base. It'll eat through any crud that's built up, especially if it's human-born, like hair and so forth, and it'll actually eat right through it. This is why dictators would use sodium hydroxide to dissolve away their unwanted citizens. And so it's also found in antacids. Now, an antacid is a medicine, a type of medicine, that removes acid that very frequently this is called heartburn, but it's not really the heart doing anything. It's your stomach acid actually, as it travels up, it can start irritating the lining of your esophagus and creating heartburn. Well, what you do is you drop a base in there, or you eat a base, which neutralizes the acid, and this is called an antacid. Bases are commonly used as antacids. Let's take a look at some things about acids and bases. Now, these can either be strong or weak. In fact, we've seen on the acids and also on the 5 bases that they're broken up into strong and weak. Now, strong acids are obviously dangerous. So in this case, you see hydrochloric acid. And weak acids aren't as dangerous as long as you have low concentrations. And vinegar is a weak base. The question is, what makes an acid strong and what makes an acid weak? So let's discuss this concept. And here is the definition of a strong acid versus a weak acid. A strong acid ionizes completely. This means that the acid completely breaks apart into ions. We'll see a picture of this in a minute. So just hold on to this definition, ionizes completely, whereas a weak acid ionizes only partially. Now, here a statement, strength is not the same as solubility. We talked about chemicals being very soluble. If a chemical is soluble and it's an acid, it does not mean automatically that it will be strong. Strength is something different than solubility. An example here, this is vinegar. Vinegar is actually, or acetic acid we said, is very soluble in water. In fact, it's very soluble because it has hydrogen bonding, but it's still a weak acid. So just because it's soluble does not mean it will be strong. And here is the picture that hopefully explains this concept a little better. What you see up at top, you have your strong acid HCl, and notice that the strong acid has broken up completely. Every molecule of acid, now the original acid you can say is like this. You have half black and half red. So this is your original HCl. And notice that any amount you put in there, all of it breaks up. Every single molecule breaks up, which means every single HCl produces an H+. Every one produces an H+. All the H pluses are in there. Whereas a weak acid, in this case the weak acid is carbonic acid, one of the ones we've discussed earlier. Most of the acid actually stays together, does not break up, does not ionize. But only a few of them break up. So this breaking up is called, again, ionization. They break up or they ionize. So, or here it says undissociated. You can also talk about breaking up, ionization equal dissociation. Dissociation. This is another fancy word that means break up. Break up. And this is the difference between a strong and a weak acid, no matter if it's a acid or a base, actually. So here are some strong acids. These are the six that we've discussed. The three strongs are hydrochloric, nitric, sulfuric. The three weaks are phosphoric, carbonic, acetic. The three strong bases are sodium hydroxide, potassium hydroxide, magnesium hydroxide. The two weak bases are ammonia and baking soda, or hydrogen bicarbonate. And you'll notice that the weak bases are the ones that have been used in cleaning. The weak acids are the ones that have been used in soft drinks and food items. The strong acids are not used in food. The strong bases are not used in food because they're much more dangerous, and so we don't use them in food. Here is another distinction, and we'll wrap this up. A monoprotic acid versus a ditriprotic acid. So if your acid has only one ionizable hydrogen, that means only one hydrogen that can be given off, it's called monoprotic. Mono for one, protic for referring to proton. And by protic, again here, is because H plus is a proton. That's why we call them protic. Ditriprotic, the same idea, except you have 2 or 3 hydrogens that can come off and ionize. This is sulfuric acid. This is a famous example of a diprotic acid. A triprotic acid would be your phosphoric acid. All right? And to be said, let's say this, most often you have just one ionizable hydrogen. Most acids produce just one hydrogen. But there are many that produce enough, or 2 or 3. And finally, let's finish up with indicators. So we've mentioned these. We mentioned 2 of these, phenolphthalein and litmus paper. But there are boatloads of different indicators out there. And an indicator is a substance that changes color in different acidic and basic solutions. So here you actually have an example of what's called a universal indicator. We have plenty of this in the chemistry laboratory, and you can actually purchase some. And universal indicator is actually set up to give you all the colors of the rainbow. Notice a lot of different colors, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different colors. Some of them are pretty similar, tough to distinguish between. But this is able to tell you not only whether it's an acid or a base, but how basic it is, how basic / acidic a substance is based on the color that it changes. Now, it's interesting that many fruits and berries in nature actually have an indicator in them. A very famous lab that we may get to do is the red cabbage lab. What you do is you take red cabbage. There's green cabbage. You grab the red one because it has the pigment. It has the indicator in it. You would boil it in water to try to boil the juices out of it. After you've done that, you would drain the juices, and then you can apply a few drops of this juice to a bunch of different solutions you find at your house. Maybe milk. You can try milk. You can try soda. You can try lemon. And what you'll see is that it'll turn all these different colors. So you can actually make an indicator that's homemade, that's able to distinguish between these different acids and bases. So we will actually get into this idea of, you see these numbers here down below, 1, 2, 3, 4, 5, 6, 7 to 12. These numbers actually mean something, and they tell you how acidic or basic the chemical is. And we will get into these in the next lesson. But for now, this wraps up for us lesson 2 of Unit 14.